All right, so we're going to prove the formula for curvature. And that formula for curvature that we're trying to prove is that curvature is equal to magnitude of r prime cross our magnitude of r prime cross r double prime over the magnitude of r prime cubed. Okay, so we'll keep that in mind. That's what we're trying to prove. Okay, curvature, as we know what curvature means. Curvature, and K is the symbol we use for curvature, is equal to basically the rate of change of your unit tangent vector over a small distance. So it's the rate of change of your unit tangent vector over a distance, an S, a length of your curve, okay? Which is fine to use this exactly as is when we have R of S, when you have your curve defined as a function of S, meaning S is the parameter. Okay, and that's not often the case that S is the parameter. Your function defined as a function of the length of your curve. Usually it's defined as a function of t or some time or some other parameter. Okay, so that's fine. This is what we use to derive this formula. But when your curve r is defined as a function of t, where t is the parameter, then we're going to take this thing and we're going to say curvature is equal to, we're going to do dt, the rate of change of your unit tangent vector with respect to t, divided by ds dt. Okay, and then we're going to go from there. Okay, now to do this, we have to remember a few things. We have to remember how you find your unit tangent vector. Okay, that's r prime of t, little t, over magnitude of r prime of little t. Or let's abbreviate that just to r prime over magnitude of r prime, assuming those are functions of t. Okay, and if we solve this thing, we also have to remember that the magnitude of r prime of t is equal to ds dt. Just a quick reminder why that's true. S is defined as your length of your, S as a function of t is defined as your length of the curve from any constant to t of magnitude of r prime of t dt. Remember, magnitude of r prime of t is that square root of dx dt squared plus dy dt squared plus dz dt squared. Okay, we abbreviate it this way. So when you take the derivative with respect to t of both sides, ds dt, dt is equal to the derivative with respect to t of any integral going from a constant to here. That just cancels out and you get magnitude of r prime of t. Okay, so this thing we will use in our formula, and this thing we will use in our proof. These two things we're going to use in our proof. So just keep those in a bubble. Keep those in the back of your head because we're going to come back to those. Okay. Now, coming from this thing right here, we're going to start with this. We can solve this equation, get the r prime by itself. So r prime is equal to the magnitude of r prime times your unit tangent vector. Okay. Remember, the magnitude of r prime, we said, is ds dt. So r prime is equal to ds dt times your unit tangent vector. Okay, and if we want r double prime, because in this formula we've got an r prime and an r double prime. Okay, so r double prime is equal to, now we've got a product rule here. Okay, so we can take the derivative of this times this, so d squared s, the second derivative of s with respect to t, times t plus this times the derivative of this. So plus ds dt times t prime. Okay, so we just did a product rule in that. Now we need to find, remember we need r prime cross r double prime. Okay, I'm going to zoom out just a little bit, sorry. Come on. Okay, not letting me zoom out anymore. Okay, but we need r prime. I'll go over here. R prime cross r double prime. Okay, so what that is, our r prime is this thing. So ds dt times t crossed with our double prime. So crossed with this entire thing. So this binomial, d squared s over dt squared t plus ds dt times t prime. Okay. And when we do that, this distributes to both of these. So we get this times this. So we get ds dt times second derivative d squared s dt squared times t cross t plus this times this. Now that's ds dt times ds dt. So ds dt squared. Don't get that confused with the second derivative of s. And then times t crossed with t prime. Okay, this is r prime cross r double prime. Let's just separate those two. Okay. Now, when we distribute, remember t cross t, that thing just ends up being 0. So this whole term goes away. So r prime cross r double prime is equal to this thing, ds dt squared times t crossed with t prime. Okay, now we want the magnitude. So the magnitude of r prime crossed r double prime. Remember why we want the magnitude. If we go back up here in the formula is a magnitude. Okay, so our magnitude of r prime cross r double prime, this thing already is a magnitude, so that we leave alone. Then we want the magnitude of t crossed with t prime. Okay, and we can simplify this. This is this thing, ds dt squared. This thing we can think of as, it's a magnitude of a cross product. So the magnitude of t times the magnitude of t prime times the sine of the angle between them. Okay. And the angle between t and t prime is always 90 degrees. Okay, now that one's a little bit tricky to understand why, but think about the set of all unit tangent vectors. I'm just going to pull out another sheet of paper. Okay, the set of all unit tangent vectors. Think of the set of all unit tangent vectors as a function of t. Well, they all have a length of 1. Okay, so you can think about, well, there's a couple ways. You can think about it this way. Unit tangent vectors, if you have the set of all tangent vectors and you put them all starting in the same place, remember vectors, you can position wherever you want. In the set of all vectors, t as a function of any t, these will make a circle. Okay. Now, if you take the derivative of anything on a circle, you get something that is perpendicular to the circle. So any one of these vectors, tangent vectors, is going to be perpendicular to t prime. Okay, so those will always be perpendicular to each other. Another way to think about this, t crossed with t prime, that t and t prime are always perpendicular to each other, is the fact that t is equal to r prime over magnitude of r prime. Okay, and then n is equal to t prime over magnitude of t prime. Okay, this is just a constant. So your normal is in the direction of t prime. And you know the tangent and the normal are always perpendicular to each other. And the normal is the same direction as t prime. Okay, so t and t prime are also normal, are also perpendicular. Okay, so this thing, sine of, we can say 90 degrees or pi over 2, okay, which is just 1. The magnitude of t is a unit vector, so that's just 1. So we get the magnitude of r prime cross r double prime is equal to ds dt squared times the magnitude of t prime. All right, and we're almost there. okay? So we also, we have this magnitude of r prime cross r double prime equals this times this, but we also know that, or if we solve this for t prime, let's come back over here. Magnitude of t prime is equal to this thing divided by this thing. Okay, remember what ds dt is. ds dt is the magnitude of r prime. So magnitude of t prime equals r prime, magnitude of r prime cross r double prime over the magnitude of r prime squared. All right, we're almost there. Well, remember what curvature equals. Curvature equals the magnitude of dt over ds dt. And we started with curvature being the magnitude of dt ds. Okay, but then we can take the dt ds with the chain rule and take dt dt over ds dt. Okay, that's curvature. Okay, which is really just the magnitude of t prime over, and ds dt is the magnitude of r prime. Remember that ds dt is just the magnitude of r prime. So I'm going to replace this thing here. So this curvature becomes magnitude of r prime cross r double prime over the magnitude of r prime squared, but then we divide by another r prime, so it's going to be divided by r prime cubed. And that's equal to our curvature. That is the formula that we wanted to prove. All right.